Good afternoon, everybody. Can you all hear me clearly? I'm not hearing anything from anybody. Are you all hearing?
Yes, sir.
Okay, good. And I'm hearing clearly too. Right. So let us start um with some more practice questions. Well, before we go into the practice questions, did you all have any questions that you all wanted to ask before we started? Okay, if not, then let us start with some more practice questions for today. So yesterday we talked about some of the experiments that led to different models of the atoms, right? But yesterday we didn't actually talk about the models of the atom. So there were some models of the atoms that we went through in class. One of them was the um the plum pudding model, right? So that was the one that was proposed after the discovery of the electron, right? So briefly describe what the plum pudding model says about the atom. That would be the question, right? Briefly describe the plum pudding model of the atom. You all have to answer before we move on to more questions.
Excuse sir.
Yeah,
It was briefly describe what the plum pudding model says about the atom. Just
yeah,
it was breaking up. Okay, thanks.
yeah. All right, so I've given you all 5 more minutes. If nobody answering anything in the 5 minutes, that means nobody want to participate and we'll end class for today. We will not do any more practice questions, right? So that's still quarter past. If by quarter past 1, nobody attempts an answer, we'll end.
So the plum pudding model states that there is a positively charged pudding and the plums, quote unquote, are negatively charged electrons. And they later on realized that that theory was wrong.
Right, so that is correct, right? The atom, according to that model, is made of thick pudding, a positively charged material. So the positively charged material were not really particles, but it was just like a pudding, something spread out. And then there was described as plums of negatively charged particles, right? So these negatively charged particles were in the pudding. So that's why it got its name, right? So that was one model of the atom. Now, after the Rutherford experiment disproved this, right? Because as we saw yesterday, the Rutherford experiment saw that the atom is comprised mostly of free space, right? Unlike the plum pudding model, where the atom is mostly positively charged and there are negative charges within that positive charge. So the Rutherford model disproved the plum pudding model, and after that, they came up with the nuclear model of the atom, right? In which there's a positively charged nucleus, and there were electrons around it. Now, the nucleus would have been a very small nucleus compared to the size of the full atom, right? Now, Bohr, as we saw in class, he tried to explain the certain colors of emission lines. Now you have seen emission lines when you did the spectrometer lab, emission lines of the mercury lamp and of sodium lamp, right? So Bohr had to explain these emission lines, and he came up with his model of the atom, the Bohr model of the atom. And in that model of the atom, so I want you all to describe Bohr's model of the atom. So when you're describing Bohr's model of the atom, I want you all to explain the terms nucleon number, atomic number, and electron shells. These three terms when you are describing Bohr's model of the atom.
So can you repeat the three terms, please? Thank you.
Nucleon number, atomic number, and electron shells.
So our Bohr models focus on how specifically the electrons behave, and it was stating that the electrons are closer to the atom in the middle, well, the nucleon with the neutrons and the protons in the middle, which is the atomic number. And they said that the electrons that were closer to that has a stronger force of attraction compared to the electrons that were further away, which are referred to the electrons that are on the valence shell. And then the nuclear number is also the mass number, and that is the total number of protons and neutrons. And then the atomic number is the protons alone.
Right. So the atomic number is the number of protons in the nucleus of the atom. Nuclear number is the number of protons plus the number of neutrons in the atom. Right. So in Bohr's model, it is similar to the nuclear model in that there's a very small positively charged nucleus comprised of neutrons and protons. But in Bohr's model, the electrons they orbit the nucleus in shells, in these electronic shells, right? The electron shells, sorry. So each shell has a distinct energy level. The word we use for that is the energy levels are quantized. So there are specific values of energy for each shell. So the first shell, which is closest to the atom, has a specific energy. The shell that is further away from that first shell, that also has a specific energy. So when electrons move between shells, they either absorb or emit specific energy, right? Specific particles of energy. And these particles of energy are photons of light, right? So this is why we see specific lines in an emission spectrum, like for example, in the mercury lamp or the sodium lamp. And also this is why we see specific absorption lines. Right? Right. Any questions? Okay, if not, let's move on to some nuclear physics now, right? So define the terms isotopes and isobars. What is the difference between an isotope and an isobar?
An isotope is two elements that have the same number of protons, aka same atomic number, but different number of neutrons in the nucleus. Whereas the isobar, they have the same mass number, but different atomic number. So it's two different elements with the same weight essentially.
Right. So yes, isotopes, they are two nuclei with the same proton number but different nucleon number. Isobars have the same nucleon number but different proton numbers, right? Right. So some other terms we saw are nuclides, right? So what is the parent nuclide and what is a daughter nuclide? Define those two terms.
So could you repeat that, please?
Define the terms parent nuclide and daughter nuclide.
So is that the parent, the original form of the isotope and the all the elements, and the daughter is the element after alpha or beta gamma decay?
Right. So not after gamma decay, because after gamma decay, the number of protons and the number of neutrons remain the same. It's
Right.
only during alpha decay, beta decay, or something else which we didn't cover in this course, which is fission and fusion. Only after these processes do the number of protons and neutrons change, right? So for this course, we did alpha decay and beta decay. So the parent nuclide would be the original nuclide before radioactive decay, and the daughter nuclide would be the new nuclide after the radioactive decay, after losing 4 neutrons, sorry, 2 neutrons and 2 protons if alpha decay occurred, or after losing a neutron and gaining a proton if beta decay occurred. Right. Another term we saw was half-life. So what is the half-life of in radioactivity? What is half-life?
The time it takes for half of the radioactive substance to decay. So for it to reduce by half, sorry.
Right. So the time it takes for half of the total amount of the radioactive substance to decay. Right. So now we did so remember we had we know that what are the mass number and the proton number. How do we write a alpha particle? What do we write as the mass number and the proton number?
Photo.
Right. So you can write it like this, right? Right. So you could write alpha particle like this. And how do we write a beta particle?
Zero,
Zero.
0 and -1.
0, -1. And we could write it as E, or 0, -1. We could write it as beta. And how do we write gamma?
0.
Right. So we could write 0, 0 gamma, or sometimes you just see gamma by itself, right? Right. So now we have alpha particles, beta particles, and gamma particles. And we know from this, the alpha particle has a charge of how much?
The 2 plus charge.
Right. A positive 2 charge, a beta particle has a charge of -1, and gamma has no charge, right? So if we have to draw these particles in a electric field, so let me draw a uniform plate here. This is positively charged, right? And here, well, this should be a proper plate, right? But so we have these 2 plates here. One is the top one is positively charged and the bottom one is negatively charged. How would an alpha particle, if an alpha particle is directed this way into towards this electric field, how would it move?
Reflect towards the negative plate.
Right, they would deflect to the negative plate. And would it be easily deflected to the negative plate, or would it travel far in the electric field and be deflected to the negative plate?
It'll travel far and then be deflected.
Right, and what is the reason it would travel far and then be deflected?
Because it's heavier than the beta particles.
Right. So the alpha particles is over 4,000 times heavier than the beta particles. So it would have a larger momentum. And because of the larger momentum, it would need a stronger force. It has a larger momentum. So for the same force, it would take a longer time to be fully deflected. So it would travel further in the field. So we could draw part like this, right? For alpha particle. Now, let's say this is a beta particle here, right? How would the beta particle move?
Towards the positive plate.
Towards the positive plate. And as mentioned, the beta particle would not move as far in the electric field as the alpha particle, right? So this is the beta particle. And let's say we have a gamma ray here, right? How would the gamma ray go?
The gamma ray will go straight down. You wouldn't have any deflections.
Right, no deflection. So it would just go straight like this, right? So, right, so this is deflection of these particles in an electric field, right? Now, if we had a positron, right? Remember, positron is just an electron with a positive 1 charge, right? How would this positron be deflected in the field?
So what was the question?
If we have a positron, so a positron, as we saw, is just an electron, but with a positive charge. Otherwise, it has all the other properties are the same. So how would the positron be deflected in this field?
The negative plate.
Right, it will be deflected towards the negative plate. And will it travel as far as the alpha particle? How far would it travel in the field?
Less than alpha, more than beta.
So it actually would not travel as far as the alpha. So you are correct, it would travel less than alpha, but it has the same mass as the beta particle, right? So it will be deflected by the same amount as the beta particle, just in the opposite direction. So we can draw this one like this, right? Well, should be the same amount. This should be at the same amount, right? For the alpha and the beta particle. Sorry, the beta particle and the positron, right? Right. This is how they would be deflected. Any questions about that? Okay. If not, let's move on to how would they be deflected in a magnetic field now. So let's say we have a magnetic field that is directed. How do we want to direct this magnetic field? We could direct this out of the sheet of the paper, right? So when we draw a magnetic field directed into the sheet of the paper, how do we draw it? What symbol do we use to draw that? A magnetic field into the sheet of the paper.
So the dot?
Right, we use dots, right? And out of the sheet of the paper would be the X's, right? So we want to have the magnetic field directed out of the sheet of the paper. That's what I said, right? Out of the sheet of the paper is dots and into is X's, right? So out of the sheet of the paper, we could draw it like this. Now let's draw another rule. Right. So if we have an alpha source, alpha particle directed towards the magnetic field, how do we determine what direction the particles move? What rule do we use to determine this?
The left-hand
Right.
rule.
Right, so use the left-hand rule, right? And in the left-hand rule, the thumb represents what?
The force.
The force, right? So the force would be the direction in which the particle would move, right? Because the magnetic force would be acting on the particle in the direction of this force, right? The index finger represents what?
The magnetic field.
The direction of the magnetic field, and the middle finger represents,
Direction of the current.
right, the direction of the current. So for an alpha particle, the direction of the current is it in the same direction of motion of the alpha particle or in the opposite direction? So basically, how do I have to orient my middle finger? Towards the right or towards the left?
They had mentioned the direction of us.
But the middle finger is the direction of the current, right? So for an alpha particle moving in the field, is my middle finger in the same direction of motion of the alpha particle or in the opposite direction?
The opposite.
No. So remember, for conventional current, which is what the left-hand rule uses, conventional current is the direction of motion of positive charges, although we know current really is the motion of negative charge, and an alpha particle is positively charged. Therefore, in this case, for the motion of the alpha particle, it would be in the same direction. The middle finger would be in the same direction of the motion of the alpha particle. So actually my video is kind of flipped compared to the screen. All right, I'll just watch the screen and do it. So the middle finger is in the direction of motion of the alpha particle. So this would be in this direction. Yeah, yeah, is opposite to what I am seeing here. Are you seeing my middle finger in the same direction as the alpha particle?
No, yeah.
Right. And then the field now is pointing out of the page. So out of the page would be, I'm pointing towards you. That would be in the page. So out of the page would be this way, right? Right. So my middle finger is that in the same motion. It might be easier just to flip my video. Let me just flip it. So my right hand, right, so my middle, you're seeing this finger in the same direction of motion of the alpha particle, right? And now the field is directed out of the page. So right, that would be like this, right? So the field is directed this way out of the page. My middle finger is directed towards the motion of the alpha particle. And the thumb would represent the direction of the force, right? So in this case, the direction of the force is downwards. So what we could do is we would draw the direction of the force on the alpha particle to be downwards. So it starts that force starts acting as soon as it enters the magnetic field, right? So it's directed this way, right? It starts making a circular motion. The initial force on the alpha particle is downwards, right? So now say we have a beta particle directed towards the magnetic field. The direction of the magnetic field is still outwards from the page, but the direction of the current changes now, right? So the direction of the current would be what direction? Would it be in the same direction as that of the electron or opposite to the motion of the electron?
Opposite.
Opposite, right? So now we would have the current moving this way, opposite to the direction of the electron, but the magnetic field would be out of the plane of the paper, so that would be this way. Right, so you can't see, let me flip it back. Sorry. Right. So the direction of the current would be opposite to the direction of the beta particle. The field would be pointed outwards, so it would be pointing right. I never had to do this on video before. Outwards towards me. Let me flip it back. Right, in the opposite direction, field is outwards, so the force would be upwards, right? You can't really see my hand the way the camera is oriented. But basically, the middle finger is pointing this way, the field is pointing outwards, and the force is pointing upwards, right? So in this case, the beta particle starts moving upwards, right? Now, will the beta particle move with the same radius of curvature as the alpha particle, or will it be smaller, or will it be bigger?
It would be smaller.
Right, a smaller radius of curvature because for the same the beta particle is much lighter than the alpha particle, so it for the same force acting on it, it will be the centripetal force will cause a smaller radius of curvature. So we could draw this like this, right? A smaller radius of curvature. Now, how would a gamma ray pass through this magnetic field? So if this is a gamma ray like this, a gamma particle, how would it pass through? How would it be deflected?
It just goes straight through like an electric field.
Right, straight through, right? Because it has no charge. So it is undeflected. Right? Because we know the magnetic force. What is the formula for the magnetic force? F is equal to B times did this at the start of the semester. We use these equations.
The BQV one.
Yeah, BQV and well sine
Sine
theta.
theta.
Right? So for the gamma particle, Q is equal to 0. Therefore, F would be equal to 0, right? So there would be no force acting on the gamma particle, so it will go straight through. Same thing for the electric field. What is the formula for the electric force? F is equal to something times E.
QE.
Q times E, right? So for the electric field, for the gamma particle, Q is equal to 0. Therefore, F would be equal to 0, so it would just go straight through. Right? Right. Any questions? Okay, if not, let us move on. Right. So so determine the number of isotopes in this in uranium. So the atomic symbol for uranium is U. So in uranium-235. So if you are given this, I want you to determine the number of neutrons in this nuclide. What formula do we need to use to calculate that?
A minus C.
Right, so N is equal to A minus Z, right? So A is equal to what?
235.
235, and Z is equal to
92.
right. So this would be how much?
143.
Right, so 143. Right, so now we have an isotope of polonium 21084, and it decays via alpha decay, right? So I want you all to tell me what do I have to write to have this as balanced um a balanced radioactive decay equation. So it decays to lead, right? And lead, we could write it as Pb. Lead has an atomic number of 82. So how can I write this if it decays via alpha decay?
So PB 206 and 82
Right? What else do I need to write?
plus alpha 14.
All right, so this is the alpha decay equation. Now, let's take an example we did before, right? So carbon 14, as we saw, is radioactive, and it's used in carbon dating, right? So let's say we have carbon 14 that has an atomic number of 6 that decays to nitrogen. So nitrogen has an atomic number of 7, right? How do we write this? So carbon 14 decaying via beta decay. What equation would this be?
So by beta diffusion, right?
Yeah,
Nitrogen 7 and 14
and then what
minus the beta, oh, plus beta negative 1 and 0.
right. So the mass number doesn't change because beta particles are very light, but the atomic number increases by 1. Right. Okay, so let's move on to some more radioactivity now, right? Electromagnetic radiation. So what is the difference between ionizing radiation and non-ionizing radiation?
Ionizing removes the electrons from the atoms, but the non-ionizing doesn't, because it doesn't have enough energy.
Right, so that is correct. So ionizing radiation is more higher energy, so those can cause electrons to be emitted from certain atoms. Right? And it creates ions basically. That's why we call it ionizing. Right. So alpha particles, beta particles, and gamma rays, they are absorbed by different types of materials, right? So alpha particles, as we know, they don't have much penetration power as compared to gamma rays, they penetrate deeply, right? So what types of material would we need to stop a alpha particle? What do we need to stop a beta particle? And what do we need to stop gamma rays?
Alpha is paper,
Right. Alpha particles can be stopped by paper. What can beta particles be stopped by? So paper cannot stop paper cannot stop beta particles. So what do we need to stop beta particles?
aluminum,
Right, a sheet of aluminum, right? And gamma particles, what do we need to stop gamma rays?
The lead.
Right, so lead is used to stop gamma rays. Um, so what are some effects of too much electromagnetic radiation on the body? So if we are overexposed to electromagnetic radiation, what symptoms can occur within the body? And who is more susceptible to these kinds of symptoms? For ionizing radiation, I should say. Ionizing ionizing electromagnetic radiation, what symptoms occur and who is more susceptible to these symptoms?
So I know that the ionizing radiation, it could damage your tissue.
Right? It could damage tissue. What else?
It could cause cancer, and children are most affected by it.
Right.
It could
It can.
also
Yeah, go ahead.
nausea.
Sorry, you could repeat that last one?
I was saying it could also cause like nausea and stuff like that in addition, but it could
Right.
also damage cells and cause cancer as well.
Yes. So ionizing radiation could cause DNA mutation, right? And this DNA mutation could cause cancer. And now because in children, cells are more rapidly multiplying when they are growing as compared to adults, they are more susceptible to these symptoms of ionizing radiation. So what are some examples of ionizing radiation?
The X-rays.
right? X-rays, that's one. Well, we talked about gamma rays, alpha and beta radiation. Okay, so what are some examples of non-ionizing radiation?
Microwave.
Right, microwaves. I heard someone else say something else, but I don't know what. What are some other examples of non-ionizing radiation?
The ultrasounds.
Ultrasound, right? So we wouldn't really consider ultrasound to be radiation, but it is a type of tool used in medicine that does not require radiation, ionizing radiation, yes. Um, what else? We have
Visible light.
visible light as well as non-ionizing, also like infrared, radio waves and so on, right? Um, right. So knowing the effects of ionizing radiation, we need to take precautions to minimize our risk of ionizing radiation, right? So what what are some precautions that we can take to minimize risk of ionizing radiation, to minimize our exposure to ionizing radiation?
So lead aprons, I think it is.
Right? So you could wear lead aprons that is basically like shielding ourselves, right? So blocking off radiation um from entering our body. That's one way. What else can we do? Like say for example, in this situation, you are a radiologist and you are administering X-rays to patients, right? And you need to minimize your exposure to radiation. So using shielding is one way of minimizing radiation. What else can you do to minimize your exposure to the radiation?
Increase your distance to the radiation exposure field.
Right, exactly. So your office could be situated very far away from the X-ray room or at the corner of the X-ray room. That is where your computer with your diagnostics could be set up. So there's a large distance between you and the X-ray source. Um, what is um, another precaution that can be taken?
Reducing your exposure time.
Right, so reducing how long you are working in that field, right? So reducing the time of exposure, or if you are the patient, you want to give the patient the minimum dose, so the minimum amount of time they would be spending in that being exposed to that radiation, right? Or if you are the radiologist, you want to spend as minimum amount of time in the room as possible to be exposed to those X-rays, right? Or any ionizing radiation. So those are just some examples, right? So it is 2 o'clock. We could take a 10-minute break and we'll start back at 10 past 2.
Excuse me, sir. When you get a chance, could you check your private message, please?
Okay. Right, so let's start back with these practice questions. Right, so when we were doing modern physics, we were looking at applications of modern physics in medicine. We dealt with some radioisotopes, right? So we were talking about the tracers. It could be used for diagnosis, and we also saw that these radioisotopes, it could also be used as a treatment, right? So, for example, we saw iodine 131 and technetium 99, right? So these were two radioisotopes we saw. So I mentioned in the coursework that you don't need to know the full detail about them, right? But this is the final exam, so you should know more detail about iodine 131 and technetium 99, right? So iodine 131, what type of radiation does it emit? Is it ionizing or non-ionizing radiation? And if it is ionizing radiation, what is it? Is it alpha, beta, or gamma particles? For iodine 131.
It's ionizing.
Right, it's ionizing radiation, yes. And is it alpha, beta, or gamma radiation?
I think it was beta.
Right, so it's actually both beta and gamma radiation, right? These are ionizing radiation. Now, is it used as a tracer or is it used for treatment primarily?
For treatment.
So actually iodine 131 is actually used as a tracer, right? So it emits, sorry, it's actually used for both treatment of thyroid cancer, and it is also used um as a for imaging, right? To take images of the thyroid gland, right? So iodine 131, it finds its way to the thyroid gland, right? And because it goes to the thyroid gland, at the thyroid, it emits beta particles and gamma rays, and since gamma rays, they can exit the body. It allows viewing of the thyroid gland, right? So how much of the iodine is deposited in the thyroid gland, and it also allows treatment of thyroid cancer, right? Because if there are cancerous cells in the thyroid, the beta particles and the gamma rays, they destroy this cancer, right? So iodine 131 is actually used for both as a tracer and as treatment. Now, what about technetium 99? Is this used as a tracer or a treatment?
As a tracer.
Right, so this is used as a tracer. So it emits gamma rays, right? It does not emit alpha radiation or beta radiation. So it emits gamma rays. These are exit the body, right? And these are detected by, as we saw, special cameras, and this allows images of the body to be formed. Now, this is used in different places to image different places, right? So for example, for heart scans, for bone scans, and kidney scans, right? So you all should remember these two radioisotopes and their purposes and uses in a little bit of detail, right? So iodine 131 and technetium 99, which we covered, but as I mentioned, for the coursework exam, it will not have been covered in detail. Right. So another question here. So you actually could be given a question in which an isotope that we did not cover came, but you will get properties of that isotope. And from those properties, you would have to talk about the suitability of that isotope in treatment, right? So, for example, if we have an isotope that emits alpha radiation, right? And it has a half-life of, let's say, 12 days. This is used to treat cancers, right? Now, just with this information alone, what are some reasons why this isotope could be used to treat cancers? It emits alpha radiation and it has a half-life of 12 days. So provide at least 3 reasons using these 2 bits of information on why this is an appropriate isotope to treat cancers.
Because it has a short half-life, it wouldn't like stay in the person's body long, so they won't be exposed to radiation for a long period of time.
Right. So after 12 days, the half of the radium is has decayed, right? So it has a relatively short half-life. After a multiple half-lives, the amount of radium would be so small that we would not have to do any type of surgery or filtering the blood to remove this radium. It would be naturally removed after a relatively short time. So that is one thing. The half-life is relatively short that we do not need to do anything for it to be removed. But the half-life is still 11 days, right? So the half-life is still long enough that the treatment would work. So it would have 11 days of the radium being used to destroy the cancer cells, right? Because it would take some time, some exposure time, to be emitting these particles on the cancer to cause the cancer to be destroyed. So the half-life is somewhere like in a sweet spot, right? It's not too long that it remains in the body and destroys healthy cells, but it's not too short that it only does the treatment for a short time and not long enough that the cancer would still remain, right? So those are two reasons, right? What is another reason that the radium could be used? So we talked about the half-life. The half-life is 11 days. Another piece of information we got in the question is it emits alpha particles. So using that piece of information now that it emits alpha particles, how can we use that as a reason for using this substance as a cancer treatment?
So does it have to do with its penetrating power?
Not exactly, no. So it emits alpha particles, right? Alpha particles are what type of radiation?
Non-ionizing.
Right, it's ionizing radiation, right? So the ionizing radiation, they would cause electrons to be removed from the atoms, right? So it basically destroys some of the atoms, and in turn, that would destroy some of the cells. So this ionizing radiation, through the emission of the alpha particles, that destroys the cancer cells, right? So being in the body for this certain amount of time, it destroys enough cancer cells that it could cause the cancer to be removed, or at least the cancer could it would not be as prevalent as before. So it has ionizing radiation that can cause the cancer cells to die. It has a half-life that is long enough so that this treatment works, but it's not too long that the radium remains in the body. So it's long enough so that the treatment works, but short enough that it naturally is removed from the body. So these are three reasons we can give based on the information that was provided to us on why this isotope is suitable for cancer treatment. So are there any questions about that? Okay, if not, let us move on. Right. So let us talk a little bit about nuclear medicine, right? So briefly explain what is a PET scan, right? So what does PET stand for, and how does this produce an image? While we're on the topic of nuclear medicine. All right, anybody? What is a PET scan?
Positron emission tomography.
All right, so that's what PET stands for. And how is that image produced?
So it basically uses a radioactive tracer. So like a small amount is injected in the patient's body, and it have like beta particles. So it will produce the image, the detailed image of their organs and whatever, like something like that.
Right. So yeah, that's the basic principle behind it, right? So um so a small amount of radioactive material is given to the person, is injected most of the time, and the radioactive material that produces gamma rays, right? And then so that radioactive material usually accumulates in certain areas, like as we saw earlier, for iodine 131, that accumulates in the thyroid gland. And that emits gamma rays, and those are detected by what we call a gamma camera. And the gamma camera that puts together the images and it view to something that we can view on a screen, right? Now, so that's basically how it works. Now, exactly what radioisotope is used in PET scans? We saw this when we did it in much more detail in the last class. So what radioisotope is used? It's a kind of long word, but we could also write it as a abbreviation with 3 letters. So what is that radioactive tracer?
So the fluoro something, FDG.
Right, FDG, right? Fluorodeoxyglucose is the radioactive tracer that's used in PET scans, right? So when that is given to the person, it's either injected into the bloodstream or the patient swallows it. And this fluorodeoxyglucose is similar to naturally occurring glucose, except it's radioactive, right? So it undergoes radioactive decay and it emits a positron, right? Which you know is the opposite of a beta particle. And then when this annihilates with an electron, it produces gamma rays, which I drew a diagram on the board explaining that. And these gamma rays are detected by a gamma camera that surrounds the patient, right? And depending on the position of the detected gamma rays, a computer analyzes this and produces an image. So different types of tissue absorb the radioactive tracer by different amounts. Cancer usually absorbs more. So by seeing the images that by looking at the image produced by the computer, we can identify cancer cells or how well healthy tissue is performing and so on, right? So that is an example of, well, that is how the PET scan works, right? Now, we talked about how the PET scan works and the tracer that's basically used and how it distinguishes between normal tissue and cancerous tissue, right? So it accumulates in more cancerous tissue than normal tissue. Now, what are some risks of these radioactive tracers?
Most of the traces are like made up of ionizing radiation. So when you're exposed to them, it could be like cancerous or like exposure could cause damage to your cells.
Right. So that is one risk, exposure to ionizing radiation. And as we saw earlier, there are many risks of um not many risks. There are many symptoms that can occur due to exposure to ionizing radiation. So that's one thing. So what is another risk?
Due to these traces either being ingested or intravenously injected, your body may not be able to excrete them if you have like liver damage, etc., etc.
Right. So that's another risk. It depends on how well your body can excrete it. It might have a longer biological half-life than expected. Even if the radioactive half-life is short, it would remain in the body. And well, also with anything that's being ingested, that it could cause allergic reactions, right? These are things that we don't usually ingest. So something new, it could possibly cause an allergic reaction. So that's another risk. Now, again, while we're on the topic of that, of nuclear medicine, sometimes radioactive treatment, radiotherapy, it could be used for care when a patient has a terminal illness, right? And for example, when they have cancer that cannot be cured, radiotherapy might still be used, right? So what are some reasons why we would use radiotherapy in this case, even when the cancer cannot be cured? So basically, it would be to improve the quality of the person's life, right? Now, in what ways does this radiotherapy increase the quality of the person's life, the remainder of their life?
It somewhat increases the lifespan, as in it gives you more time. And it slightly treats some of the cancer cells, so it wouldn't be as harsh, I want to say. So it wouldn't be like full on the full strength of it as compared to if you were doing radiotherapy.
Right. So those are two reasons. It can extend the lifetime of the person. It would also reduce the amount of pain because um it does damage some of the cancer cells. What is another reason? Well, actually, that one we could say is two reasons, right? So it reduces the size of the cancer, and by doing that, it relieves pain and symptoms, right? And by doing that, it also extends the life expectancy. So we could write um those points as three different points, I should say, right? So it reduces the size of the cancer, it helps with pain relief, and it extends life expectancy, right? Right. So let us do one calculation. So let's say, okay, radium has, I'll write it out. Sorry. Right. So radium-223 has a half-life of 12 days, right? Now, let's say a sample in the hospital, it had 60 not 60, let's say 50 milligrams of radium. So sample initially contained 50 milligrams of the radium, right? Now calculate how much of the radium would be in the sample after 36 days. Right. So how do we go about doing this question? And well, this would have to be the last question for the day because we run out of time. We didn't get to cover anything on diagnostic tools, right? So like, for example, X-rays, fluoroscopy, CT scan, MRI, ultrasound, mammograms. I had some more questions to do on those, but well, a lot of time was spent waiting, right? So all of those we did not get to cover, so you all will have to cover those yourself, right? So you have the notes, you have the tutorials, and well, you went on the field trip last week and this morning, right? So on the field trip, you would have seen how they work, you would have had explanations on the advantages, disadvantages, and so on, right? So you should be okay with those for the exam as well. Right, but back to the question, let's finish this question and then that would be it for today.
We could find the number of half-lives that went through over the 36 days.
Right, so yes, we could do that. So after 36 days, how many half-lives occur? Right, so what I writing in the blank here?
It would be 36 divided by 12, so 3.
Right. So 3 half-lives elapsed, right? So therefore, the remaining remaining mass of radium-223 is equal to 50 times how much?
A half to the power of 3.
Right, times a half times a half times a half, because if every half-life we multiply by a half. So this is equal to 50 times a half to the power of 3. Right. So this is really how much is this? 25, 12.5, 6.25. Is this correct?
Yes, sir.
Right, 6.25, and unit would be how much? Unit would be what, sorry?
Milligrams.
Milligrams, right? Because the mass they initially gave us was 50 milligrams. So, right, so that's it. Right, we run out of time to do any more questions. So yeah, so that's it for today. Well, and this is our last class for the not just the semester, the entire academic year. I will have to schedule some remedial classes for those who have to repeat semester 1 and semester 2 courses. So I will have to talk to the admin about that, because I know you all would have remedial classes for the other courses as well, and we only have 1 week we could schedule those classes in. So I do have to speak to them about that and see when I could fit in time to do a remedial class. So I'll do that and finalize the dates, and then I will let your class reps know, and we'll schedule some dates for remedial classes. So we have 5 hours of remedial classes for semester 1 and 5 hours for semester 2. Now, the plan is to do it just like this, so we'd have questions and you all could answer it. So that way you will get practice. It will be like a mock exam basically, and I will be guiding you through the answers. Well, helping with correcting the answers basically, right? If need correction, or just writing down the answers. Ideally, it would just be writing down the answers. So I'll schedule those dates with you, and hopefully for those remedial classes, we could get more questions done than what we did today, right? Because yeah, we didn't get to finish. Like, the amount of questions we did over these past 2 days in these 5 hours is still not like equivalent to 5 questions you would do in an exam in 3 hours, right? We took much longer to do these questions. This would be equivalent to like 4 questions, say, because as I mentioned, we didn't do any of the imaging techniques other than like PET scan, right? So hopefully for those other 2 classes, we do it much quicker, right? Right, so yeah, for those who are not repeating, I guess this would be last time I am seeing you all. And so I wish you all the best in your exam, and wish you the best in the future, right? So if there are no more questions, I guess we could close for today.